Tonight on Space Science, the sky over the United States reveals a mystery that has become harder to ignore. In recent years, strange fireballs have appeared with unusual frequency, some fading quietly, others bursting with enough force to shake homes and rattle windows. Scientists say these events are real, measurable, and not always easy to dismiss as ordinary. This documentary follows their path from deep space to Earth's atmosphere to understand what they are, where they come from, and why some experts are paying closer attention. Before settling in, please like the video, subscribe to Space Science, and turn on notifications for more calm journeys through the wonders and mysteries of the universe. Across the United States, the night sky settles into place with quiet regularity. It stretches over deserts, plains, forests, coastlines, mountain ranges, river valleys, and cities of every size. In some regions, the darkness arrives slowly, with a long afterglow lingering above the horizon. In others, it comes more abruptly, as if the land simply turns away from the sun and leaves its surface to cool beneath a wide dome of air. The sky itself does not change in purpose from one state to another, yet its appearance shifts constantly with weather, season, elevation, humidity, and the amount of artificial light rising from the ground. Before any bright object crosses that darkness, the setting is already full of detail, and it is within that broad visible setting that reports of fireballs begin. Over remote western basins, the sky often appears deep and open, with stars seeming numerous and sharp. Over humid southern lowlands, the darkness may look softer, with a faint haze spreading light and reducing contrast. Along the eastern seaboard and across large metropolitan corridors, the glow of human settlement lifts upward and washes the lower sky in pale orange, white, or bluish tones. This upward spill of light, known as light pollution, reduces the number of stars visible to the eye. It does not remove the sky, but it changes what a person can notice within it. In darker places, a faint streak may stand out clearly. In brighter places, only the most luminous events attract immediate attention. Clouds also shape the visible world above. A completely clear sky is less common than memory sometimes suggests. Thin, high clouds can blur stars without hiding them. Lower cloud layers can erase whole regions of the sky and leave only broken openings between drifting masses. In winter, cold, dry air over parts of the interior can create striking transparency, while in summer, moisture and heat can soften the entire vault overhead. Smoke from wildfires, dust lifted from dry ground, sea salt carried inland, and industrial aerosols can all add fine suspended particles to the air. These small particles scatter light, which means they redirect it in many directions. The result can be a sky that glows more than expected near towns and roads, or a horizon that remains luminous long after sunset. The moon has an equally strong influence on what is seen. When it's near full, it brightens the landscape and dims the background stars. Shadows become visible on open ground. Familiar constellations remain, but fainter stars withdraw into the brightness. During a moonless period, by contrast, the sky can seem far deeper, and a watcher becomes more aware of subtle changes in darkness and motion. The same physical event in the sky may therefore appear very different depending on lunar phase. A brief streak that feels dramatic under moonlight might look even more intense under a dark sky, while a modest event can pass unnoticed when the moon and city lights combine to reduce contrast. Ordinary celestial objects establish the baseline against which unusual lights are judged. Planets shine steadily and do not usually flicker as much as stars. Bright stars near the horizon can appear to flash in shifting colours because their light travels through a thicker layer of turbulent air. Aircraft move with a more gradual pace and usually display repeated navigation lights. Satellites cross the sky smoothly, often without blinking, and sunlight may briefly flare from their surfaces. In rare cases, space hardware re-entering the atmosphere can produce a more complex and prolonged display. Yet most nights contain no dramatic event at all. They hold only the steady turning of Earth, the rising and setting of known objects, the passage of clouds, and the subtle awareness that the atmosphere is never entirely still. Human perception plays an important role in this setting. The eye adapts slowly to darkness, becoming more sensitive over time. A person stepping outside from a bright room may see only the moon and a few strong stars at first. After several minutes, many more points of light become visible. The brain also interprets motion quickly, sometimes too quickly, because sudden brightness or unexpected movement naturally draws attention. A bright planet low on the horizon can seem larger than it is. A distant aircraft seen through thin cloud can appear strange for a moment. The night sky is therefore both a physical environment and a perceptual one. Reports of unusual lights arise not only from what is present overhead, but also from how conditions on the ground shape visibility and expectation. Across the United States, modern observation has added another layer to this visible setting. Doorbell cameras, dashboard cameras, security systems, mobile phones, weather cameras, and dedicated all-sky instruments now watch the sky far more often than human observers alone ever could. Many devices operate automatically. Some face streets and parking lots, yet still capture a bright streak reflected on pavement or briefly crossing the upper edge of a frame. Others are designed specifically to record the entire sky through the night. This means that the visible setting over the country is no longer witnessed only by isolated individuals looking upward by chance. It is increasingly sampled by networks of instruments, each limited in its own way, but together forming a broad record of what passes through view. Still, the night remains unevenly observed. Vast rural regions may have dark skies but few cameras. Dense urban zones may have many devices but poor visibility near the horizon. Weather can cover one state while a neighbouring state remains clear. An event that appears striking in one location may be hidden entirely in another. The same sky, spread over a continent-scale nation, is therefore never experienced as a single uniform field. It is a patchwork of local conditions. When accounts later gather around one bright event, those accounts come from different skies beneath the same atmosphere. In this broad setting, the term fireball has a specific meaning in astronomy. It refers to an exceptionally bright meteor, generally brighter than the planet Venus in the night sky. A meteor is the visible streak produced when a small natural object from space passes through Earth's atmosphere and generates light. The definition belongs to observation, not emotion. A fireball may inspire surprise, but it is not defined by surprise. It is defined by brightness. That brightness must first be noticed against darkness, cloud, haze, moonlight, and competing human light. The sky over the United States provides all of these conditions in varying measure, which is why public experience of fireballs is so uneven. Before any explanation turns to space, stone, speed, or heat, the visible stage must remain simple. There is land cooling after sunset, air layered above it, and an overhead field whose clarity changes from place to place and night to night. There are stars, planets, satellites, aircraft, clouds, and the soft distortions of perception. There are also cameras, records, and many eyes that look up only when something unusual interrupts the expected calm. The night sky is not empty, and it is not uniform. It is a shifting screen of darkness and light, delicate in some places, washed out in others, and always dependent on the air through which it is seen. Within that ordinary setting, a fireball becomes visible first, not as an explanation, but simply as a sudden brightness moving across a familiar sky. Beyond the visible sky over the United States, beyond the clouds and the light scattered in Earth's air, the planet moves through a much larger environment filled with small solid bodies. Space near Earth is not crowded in the ordinary sense, and it is mostly empty by human standards. Yet it is not empty of matter. Fine dust, small grains, pebble-sized fragments, and larger rocky pieces travel through the inner solar system along their own paths around the Sun. Some of this material has done so for immense spans of time. Some has been released more recently by collisions or gradual shedding from larger bodies. Earth continues along its orbit through this wider field, and in doing so it regularly encounters natural debris of many sizes. This surrounding population includes particles far smaller than sand, and objects large enough to survive passage through the atmosphere in part or in full. In space, before any contact with air, such bodies are called meteoroids. The word refers to a small natural object moving through interplanetary space. It does not describe light or flame. It simply describes a piece of matter in transit around the Sun. Most meteoroids are modest in size. Many are tiny. A smaller number are large enough to produce more striking effects if they meet Earth under favourable conditions. Their motion is governed by orbit, which is the repeated path an object follows under the pull of gravity. In the inner solar system, the dominant pull belongs to the Sun, though planets also shape the long-term behaviour of smaller bodies. Earth itself is not motionless within this setting. It travels around the Sun at about 30 kilometers per second, while also turning on its axis once each day. This planetary motion matters because any encounter between Earth and a meteoroid depends not only on the speed of the meteoroid in its own orbit, but also on the relative geometry between both paths. A body moving in a similar direction to Earth may meet the atmosphere at a lower relative speed than one arriving from a very different orbital direction. The result is that incoming objects do not all approach with the same energy. Some are comparatively slow by meteor standards, while others arrive at extremely high speed. Scientists measure this carefully because speed strongly affects how bright a meteor becomes, how high it first appears, and how likely it is to survive deeper descent. The space around Earth also contains many bodies that never come close enough to encounter the atmosphere. Their paths remain safely distant. Others cross Earth's orbit but arrive when the planet is elsewhere along its yearly journey. Orbital crossing does not guarantee contact. It creates only the possibility. The timing must also match. Earth therefore moves through a changing pattern of potential encounters, some regular and well understood, others more scattered and less predictable. At any moment, countless small bodies continue around the Sun without interacting with the planet at all. Only a very small fraction ever meet Earth directly. Much of this material has ancient origins. Some meteoroids are fragments of asteroids, which are rocky or metallic bodies that orbit mainly between Mars and Jupiter, though some follow paths that bring them closer to Earth. Collisions among asteroids can break them into smaller pieces over long periods. Gravitational nudges and subtle effects related to sunlight can shift fragments into new orbits. Other meteoroids are associated with comets, bodies that contain dust, rock, and frozen volatile substances such as water ice and carbon dioxide ice. When comets approach the Sun, Warming can release dust and small particles into space. These particles may remain distributed along the comet's path for long periods. Some eventually intersect Earth's orbit and become the source of repeated meteor activity during certain times of year. The near-Earth region is therefore not a static shell of debris around the planet. It is better understood as a crossing zone within a dynamic solar system. Earth moves through it. Meteoroids move through it. Orbits stretch, tilt, and overlap in many ways. Gravitational influences from planets, especially Jupiter over long timescales and Earth over shorter local encounters, help shape these paths. The result is a natural background of possible atmospheric entries. This background is not a sign of disorder. It is a normal consequence of the solar system's history, in which collisions, fragmentation, and orbital evolution have been active for billions of years. Even so, the distribution of material is not uniform. Some regions of Earth's orbit are associated with denser streams of small particles left by comets. Other encounters come from isolated fragments, whose parent bodies are harder to trace with certainty. A given night over the United States may coincide with no significant increase in incoming material, or it may occur during a known meteor shower, when Earth passes through a stream of debris and visible meteors become more common. Yet even outside these familiar periods, sporadic meteors continue to occur. The term sporadic in this context means not tied to a recognized shower. It does not mean impossible to explain. It means that the object belongs to the broad background population rather than to a clearly identified stream. From far outside the atmosphere, Earth presents a small target. Its cross-section is limited relative to the vastness of space. Still, because the planet has a substantial size and moves continuously along its orbit, it sweeps through interplanetary dust and debris over time. A useful image is that of motion through a very thin natural drift of particles, though the comparison must remain gentle, because the density in space is far lower than anything familiar in air or water. There is no resistance in the ordinary earthly sense. There is no visible cloud surrounding Earth. Yet over long intervals the planet does encounter matter steadily enough that meteors are a routine part of the natural environment. Scientists study this surrounding population using telescopes, radar, recovered meteorites, photographic records, video networks, satellite observations, and models of orbital dynamics. These methods show that Earth is continually exposed to a rain of extraterrestrial material, most of it very small. Larger objects are much less common. This difference in abundance is important. Tiny grains enter often and usually pass unnoticed, except by specialized instruments. Brighter meteors require somewhat larger particles or especially favorable speeds. Fireballs usually involve larger incoming bodies than ordinary faint meteors, though still often modest in size compared with the public imagination. A rock no larger than a grapefruit can in some cases produce a very bright event, depending on its composition, speed, and path. Within this wider region, nothing yet glows, nothing yet burns in the everyday sense. The objects remain cold by comparison with atmospheric entry, lit only by sunlight when exposed and otherwise drifting in darkness. Their surfaces may be fractured, dusty, metallic, porous, or compact. Some rotate slowly, some tumble, some have travelled undisturbed for ages since their last major collision. Others are younger fragments. All remain part of the quiet outer setting of the topic. Earth moving through near-Earth space, and near-Earth space containing the small natural bodies that sometimes meet the planet's path. Before a fireball becomes a streak of light over the United States, it begins here as an unnoticed meteoroid following an orbit around the Sun within the thin but persistent debris environment of the inner solar system. Within the wider population of small bodies that cross Earth's orbital region, not all arrivals are of the same kind. Some belong to organized streams of debris that return in a regular pattern each year as Earth passes through them. Others come from no obvious stream at all, and appear as independent arrivals scattered through time. This difference matters because the sky can seem more active during certain periods without any change in the basic physics of atmospheric entry. The source population changes, and with it the visible rhythm of meteors. To understand why some fireballs appear during recognized seasons of activity, while others arrive alone, scientists separate these sources into broad categories before the atmosphere enters the story. A meteor shower is produced when Earth passes through a trail of particles distributed along the orbit of a comet, or in some cases a body that behaves like an extinct comet. A comet is a small solar system body made of rock, dust, and frozen materials. As it approaches the Sun, warming releases gas and embedded dust. Over repeated passages, this material spreads along the comet's orbit and forms a long stream. The particles in such a stream are usually small, often no larger than grains or pebbles, though some larger fragments can also be present. When Earth intersects this path, many of the particles enter the atmosphere from roughly similar directions. To an observer on the ground, their tracks seem to radiate outward from one area of the sky. That apparent origin point is called the radiant. It is an effect of perspective, not a physical source in the sky. Known showers return because Earth's orbit meets the same debris stream at nearly the same point each year. The Perseids, Leonids, Geminids, and other established showers are examples of this regularity. Their activity can vary from year to year because the density of particles in the stream is not perfectly uniform. Some regions are richer, some thinner. Gravitational effects from planets can gradually shift the stream, and old dust trails can spread out over time. The result is that one annual return may be stronger than another even though the shower itself is familiar. Most shower meteors are not fireballs. Many are faint, brief, and numerous rather than individually dramatic. Yet some showers are known to produce a proportion of brighter events, depending on the size and structure of the particles in the stream. These organized streams represent one kind of source, but they do not account for everything seen in the sky. Outside the recognized showers, Earth is continually struck by sporadic meteoroids. These arrive from the general background population of debris in near-Earth space. Their directions are more varied, and their timing is not tied to a single calendar peak. Some sporadic meteoroids may still have ancient cometary origins, but their paths have become mixed and dispersed enough that they no longer form a clearly identifiable shower. Others are fragments from asteroids that entered Earth-crossing orbits after collisions and long orbital evolution. In practical observation, the term sporadic simply marks an event as not belonging to a recognized active stream. It does not suggest that the object is rare or mysterious. In fact, sporadic meteors make up a substantial part of ordinary nightly activity. Asteroidal fragments differ from typical cometary dust in important ways. Asteroidal material is often denser and more compact. It may contain silicate minerals, metal, or a mixture of both. Cometary particles are often more fragile and porous, though there is wide variation in both groups. This difference in material strength can influence how a meteoroid behaves later in the atmosphere, but even before entry, it helps explain why the source populations are not uniform. A stream derived from a comet may contain many small weak particles spread along an orbit. A fragment from an asteroid may arrive as a more isolated object, part of no visible shower, yet large enough and strong enough to create a bright fireball if it encounters Earth under the right conditions. There is also a mixed and evolving middle ground between these categories. Some near-Earth objects blur the line between asteroid and comet. A few bodies appear asteroidal in telescopes, yet may be dormant cometary remnants, having lost much of their near-surface ice after many passages near the Sun. Others may have characteristics that reflect a complex history of heating, fragmentation, and surface change. In the study of meteoroid sources, clear boundaries are useful. But nature does not always respect simple labels. Scientists therefore speak cautiously when linking an individual fireball to a specific parent source. If a meteor appears during a strong shower, and its path matches the shower's geometry, the association may be straightforward. If it appears outside known shower activity, the origin is often assigned more generally to the sporadic background unless further orbital reconstruction is possible. Orbital reconstruction is the process of estimating the incoming path of a meteoroid before it enters the atmosphere. This can be done when multiple cameras or instruments record the event well enough to determine its trajectory and speed. From these measurements, scientists can calculate an approximate pre-entry orbit around the Sun. Sometimes this reveals a likely asteroidal type of orbit. Sometimes it shows similarity to known streams. Sometimes the uncertainties remain too large for confidence. This is one reason that public impressions of sudden clusters can be misleading. A bright event on one evening and another a few nights later may look connected to local observers, yet the objects may come from entirely different orbital populations. Randomness in human experience also shapes the sense of pattern. A truly isolated arrival can appear especially meaningful if it follows news coverage of another fireball. A shower night may produce many ordinary meteors, but only one especially bright one draws widespread attention. A period of cloudy weather can hide most activity. Then a single clear evening reveals several events that would otherwise have passed unnoticed. Scientists therefore distinguish between the physical pattern of meteoroid arrival and the observational pattern of human reporting. The first depends on orbital populations and encounter geometry. The second depends on weather, darkness, technology, and attention. The word random is often used loosely in public discussion, but in this setting it requires care. A sporadic meteoroid does not arrive without cause. Its motion is still governed by orbital mechanics. Its encounter with Earth still follows from the geometry of two paths round the Sun. It appears random mainly because it is not part of a predictable annual stream obvious to observers on the ground. There is order in the background, but it is the order of many overlapping orbits rather than the cleaner occurrence of a meteor shower. That distinction helps explain why some fireballs seem to belong to a known season, while others arrive with no public warning at all. At this stage, the topic remains outside the atmosphere. The sky over the United States may later record a sudden brilliant streak, but the source story begins with populations of particles and fragments in solar orbit. Some are arranged in streams left by comets and revisited each year. Some are isolated or widely dispersed pieces, often linked to asteroidal fragmentation or long mixed debris populations. Together they create a natural range of arrivals, from clustered activity to solitary events. The difference between shower meteors and sporadic arrivals is not a difference between normal and abnormal nature. It is a difference between organized source regions and the broader background of matter through which Earth continues to travel. High above the United States, above clouds, aircraft routes, and the weather systems that shape daily life, the outer atmosphere forms the first physical boundary between Earth and a small body arriving from space. This region is extremely thin compared with the dense air near the ground. It cannot be breathed, and it does not behave like the lower atmosphere that carries wind, rain, and dust across the land. Yet even this rarefied upper layer is enough to begin changing the fate of an incoming meteoroid. The object has travelled through space in near vacuum, guided by gravity and orbit, but here it begins to meet resistance from gas. The contact is not like striking a wall. It is a rapidly increasing interaction with atoms and molecules in the atmosphere, minute by minute in altitude, and then moment by moment as the descent continues. The upper atmosphere includes regions where the air is so thin that the distance between particles is large by everyday standards. Even so, a meteoroid entering at cosmic speed encounters those particles with enormous relative energy. The incoming body does not need dense air to begin changing. Speed alone makes the early contact significant. The atmosphere at these heights is made mostly of oxygen and nitrogen in extremely low density, along with smaller contributions from other gases. To the human eye from the ground, this region seems like empty sky. To a fast-moving meteoroid, it becomes the first place where its motion begins to disturb the gas around it in a measurable way. This first contact is often misunderstood as ordinary friction, as if the body simply rubs against air and becomes hot in the same way hands become warm when pressed together. The actual process is more specific and more intense. A meteoroid moving at many kilometers per second compresses the gas in front of it. Compression means that the gas is forced into a smaller space. When gas is compressed rapidly, its temperature rises. The air in front of the body becomes extremely hot, and this heat contributes strongly to the changes that follow. At the same time, collisions between atmospheric particles and the surface of the meteoroid transfer energy directly into the outer layers of the object. The result is not gentle warming, but a rapid and severe thermal stress concentrated at the front and surface. The height at which this process begins depends on several factors. Speed is one of the most important. A faster meteoroid begins producing stronger atmospheric effects higher up, because each collision with thin air carries greater energy. Composition also matters. A fragile porous body may begin to shed material earlier than a compact and denser one. Entry angle matters as well. An object descending steeply passes through atmospheric layers more directly, while one arriving at a shallower angle travels farther through thin upper air before reaching denser levels. Size affects the balance too. Very small particles can be slowed and consumed high above without producing a bright fireball, while larger bodies can maintain enough momentum to continue deeper. These factors work together, so there is no single fixed altitude at which every meteoroid begins to behave in the same way. At first, the changes may be invisible to people on the ground. A meteoroid can begin to interact with the upper atmosphere before it becomes bright enough to notice with the unaided eye. Its leading surface starts to heat, and microscopic grains or minerals at the exterior may weaken or detach. In many cases, the surface begins to melt. Some of this molten material is then swept away by the rushing flow around the body. This removal of surface material is called ablation. Ablation means loss of mass from the exterior through heating and erosion during atmospheric entry. Once the term is defined, the process can be understood plainly as the gradual stripping away of the outside of the object under extreme conditions. It is one of the central reasons meteoroids change so quickly as they fall. The upper atmosphere does not merely receive the incoming object, it reacts to it. As the compressed gas heats and becomes excited, the region around the meteoroid turns into a short-lived disturbed zone. Molecules can break apart, atoms can lose electrons and become ions, which are electrically charged particles. This ionized gas is often called plasma. Plasma is not a special flame in the ordinary sense. It is a state of matter in which gas has been energized enough that charged particles and free electrons are present. Around an entering meteoroid, plasma forms because of the high-energy interaction between speed, air, and heat. The disturbed zone can extend around and behind the object, especially as ablated material mixes with atmospheric gas. Even in this early stage, the event is not yet a simple falling rock. It is a coupled system involving the body and the air around it. The meteoroid's speed compresses and heats the gas. The hot gas transfers energy back to the surface melts, sheds material, and releases atoms into the flow. Those atoms may also become excited or ionized. The body loses mass while the surrounding gas becomes luminous under the right conditions. This interaction is why scientists treat atmospheric entry as both a physical and a chemical process. Minerals in the object, metals in the object, and gases in the atmosphere all begin to participate. The exact balance depends on the original material. Some meteoroids contain minerals rich in iron and magnesium. Others include metal phases or more fragile carbon-rich material. These differences influence how easily the surface melts and how the body responds to stress. The scale of the object often surprises the public. A fireball does not require a very large body by terrestrial standards. Because the speed is so high, even a modest stone can release substantial energy into the air and produce a bright event. The energy comes mainly from motion. A moving body carries kinetic energy, which is the energy of motion. When the atmosphere begins to slow the meteoroid, some of that energy is transferred into heating, light, sound later on, and mechanical breakup. The upper atmosphere is therefore the beginning of transformation from silent orbital motion into a visible atmospheric event. Nothing supernatural occurs there. The process is severe, but it follows known physical laws. At these altitudes, the object is also still travelling much faster than any ordinary aircraft or weather phenomenon. This alone distinguishes the event sharply from familiar motion in the sky. The body may still be intact, or it may already be weakening internally as heat and pressure stresses build. Small fractures present from ancient collisions in space can matter now. Differences in mineral grain size can matter. Internal voids can matter. The atmosphere is thin, but the demands placed on the body are enormous because they rise so quickly with speed and compression. Some meteoroids remain coherent for a time. Others begin to shed grains, crack, or partially fragment very early. What the upper atmosphere does, then, is not merely start a descent. It initiates conversion. A quiet meteoroid in solar orbit becomes an entry body under stress. Its outer surface begins to change from solid exterior to flowing and stripped material. The gas ahead of it becomes compressed and hot. Charged particles appear in the disturbed flow. The object is no longer simply in space, yet it is not yet part of the lower atmosphere familiar from weather and wind. It occupies a narrow physical stage high above the country, where air is still thin but no longer negligible. In that high region, first contact is complete motion has met atmosphere, and the long silent path through space has begun to turn into an event shaped by gas, heat, pressure, and loss of material. Once the incoming body has begun to disturb the upper atmosphere, the event becomes visible through light. This light is the feature that turns an unseen entry into a fireball recognized from the ground. It appears sudden to human observers, yet it is produced by a chain of physical changes already underway. A meteoroid enters the upper air at very high speed, compresses the gas in front of it, heats that gas strongly, loses material from its surface, and surrounds itself with a short-lived region of hot and excited matter. The visible streak is the result of that region radiating energy as light. A fireball is therefore not simply a rock glowing on its own. It is a moving interaction between the body and the atmosphere, and the brightness comes from both. The first source of visible light is the heated air itself. As the gas around the meteoroid is compressed and energized, atoms and molecules are excited into higher energy states. An excited state means that a particle has absorbed energy and is temporarily holding it. When that particle returns to a lower energy state, it releases energy, often in the form of light. This is one reason meteor light can appear quickly and intensely, even at high altitude where the atmosphere is thin. The air has not caught fire in the ordinary sense. Instead, it has been forced into a hot luminous state by compression and collision. Nitrogen and oxygen, the main gases in the atmosphere, contribute to this glow in ways that depend on temperature, pressure, and the exact path of the event. A second source of light comes from the meteoroid itself as it loses surface material. During ablation, melted and vaporized matter is stripped away and mixed into the flow around the object. That material includes atoms from minerals and metals that were once part of the original body. These atoms can also become excited and emit light at characteristic wavelengths. In careful instrumental observations, scientists can sometimes detect signatures from elements such as iron, magnesium, sodium, and calcium. Each contributes to the glow in its own way, though the human eye usually sees only a blended brightness rather than distinct lines of colour. The visible fireball is therefore a mixture of atmospheric light and material light, with the relative balance changing as the event evolves. This helps explain why the common phrase burning rock is only partly useful. The event does involve intense heating, but not simple burning like wood in air. Ordinary burning is a chemical reaction with oxygen that releases heat through oxidation. Meteor light is dominated instead by compression heating, vaporization, ionization, and radiative emission from excited gas and ablated material. Some oxidation can occur in the hot flow, especially deeper in the atmosphere, but it is not the main reason the meteor shines. Scientists describe the visible trail as a luminous phenomenon produced by atmospheric entry, not as a familiar open flame. The distinction matters because it keeps attention on the real process rather than on a misleading image. Brightness depends on how efficiently kinetic energy is converted into visible radiation. Kinetic energy is the energy of motion. A fast meteoroid carries a great deal of it, and as the atmosphere begins to slow the body, some of that energy is transformed into heat, light, and mechanical disruption. A larger body usually provides more total energy, but speed can be equally important or even more important for the visible effect. A small, fast object may outshine a larger, slower one. Composition also matters. A fragile object that breaks apart early can spread energy through the air differently from a dense object that stays intact longer. The visible intensity of a fireball is therefore not determined by size alone. It is determined by a combination of mass, speed, structure, and entry path. To observers on the ground, this light often appears as a streak, a flare, or a bright moving point with a trailing line. The exact appearance depends on distance, atmospheric clarity, and the geometry of the path. A fireball far away may look like a brief silent line. A nearer one may show changing brightness, a swelling head, or a glowing trail that lingers for a few moments. The head is the brightest forward region associated with the moving body and its compressed luminous envelope. The trail behind it may include glowing gas, ionized material, and fine particles left in the wake. Some trails fade almost at once. Others persist longer and are gradually twisted by high-altitude winds. These persistent trains, as they are called, are not the meteoroid itself. They are disturbed material and gas remaining after the brightest passage. The colour of the light can vary. Some fireballs look white, bluish-white, yellow, orange, or greenish. Colour depends on several interacting causes. Temperature affects the general balance of emitted light. Atmospheric gases contribute in one way, while vaporized meteoroid material contributes in another. Sodium can add warm yellow tones. Magnesium can contribute bright greenish light in some conditions. Ionized gas can create cooler or more bluish appearances. Human vision also plays a role because the eye does not judge colour equally well at night. A rapidly moving bright source against darkness can seem whiter or more washed out than it would in precise instrumental data. Even so, colour can provide useful clues when combined with measured speed and trajectory. The visible onset of a meteor does not mark a single universal height. It begins where the conditions become sufficient for sustained luminous emission. This threshold changes from event to event. Fast, fragile particles may begin glowing high above the denser atmosphere. Slower or stronger bodies may become prominent somewhat lower. Fireballs often remain visible across a substantial altitude range, as long as the interaction continues to produce enough light. During this time, the body is losing mass, changing shape, and experiencing strong mechanical stress. The brightness may rise and fall as material sheds unevenly or as the object rotates. In some cases, a brief flare marks a sudden increase in ablation or the beginning of fragmentation. In others, the light remains comparatively smooth. Observation networks use the brightness record, called a light curve, to study these changes. A light curve is a measured record of how brightness varies over time. It allows scientists to estimate when energy release becomes stronger, when fragmentation may occur, and how the body behaves as it descends. This is one reason a fireball is scientifically valuable even when no meteorite is ever recovered. The light carries information. Its duration, intensity, colour, beginning height, and end height all help reconstruct the nature of the incoming object and the conditions of entry. From the ground, the event may seem like a sudden interruption of the ordinary night sky. In physical terms, it is the moment when invisible orbital motion becomes visible atmospheric radiation. Light is the first widely shared evidence that the encounter is happening. It reveals neither the full size of the body nor its exact origin by sight alone, but it shows that gas and matter high above the country have entered a state of intense excitation. The fireball shines because air is compressed and heated, because the meteoroid sheds and vaporizes material, and because those hot excited particles release energy as light. What appears as one bright streak is in fact a moving zone of transformation, luminous for only a brief interval, yet clear enough to turn a silent descent in the upper atmosphere into an event seen across cities, fields, highways, and dark open land. As the fireball continues across the sky, its visible behavior begins to reveal more about the incoming body. The streak is not only bright, it moves with a certain speed across the field of view, follows a particular angle, shifts in brightness, and sometimes changes colour from one part of its path to another. These features do not arise at random. They reflect the interaction between the object's motion, the structure of its material, and the growing pressure of the atmosphere. In this stage of the event, the fireball becomes a moving record of change. The eye sees a line of light, but the line contains clues about velocity, composition, and breakup. Speed remains one of the central controls. Meteoroids enter Earth's atmosphere over a wide range of velocities, from relatively slow encounters to extremely fast arrivals. The higher the entry speed, the more violently the body compresses the air ahead of it, and the more rapidly energy is transferred into the surrounding gas and into the surface of the meteoroid itself. This tends to make the meteor brighter earlier and at higher altitude. Faster entries also often produce more abrupt visual behavior because the heating and stress rise quickly. Slower entries can still create bright fireballs, especially if the body is large enough, but the light may build in a somewhat different way and the visible path may last longer. To an observer on the ground, speed is often hard to judge accurately by eye, because distance is rarely obvious at night. A very distant fast event may seem modest, while a closer one can appear almost impossibly swift. The angle of entry also shapes what is seen. A steep path carries the body more directly downward through atmospheric layers. This usually shortens the visible track in geometric length, though the event may still be very bright. A shallower path lets the object travel across more of the upper atmosphere before reaching denser air. Such a fireball can appear to glide for a long distance across the sky, especially if seen from far away. This does not mean it is moving gently. It remains a high-speed event, but its geometry spreads the luminous path across a broader arc of view. Shallow entries may also prolong the period during which the body loses mass and undergoes stress, because the descent through denser air is less abrupt. The visible effect can therefore seem smoother at first, followed later by stronger flaring or fragmentation. Color becomes more noticeable as brightness rises. Many fireballs look white for much of their path, because intense light tends to overwhelm subtle color differences in human vision. Yet observers often report green, yellow, orange, blue-white, or red tones, especially during the brightest moments or in the wake. These colors reflect a mixture of physical causes. Different atoms emit light at different wavelengths when excited. Sodium often contributes yellow light. Magnesium can contribute greenish tones. Iron can add to a broader white or yellow-white impression. Atmospheric gases in the hot shocked region also emit light, and the temperature of the flow affects the balance. A cooler fading end may appear warmer in color than a sharply brightened early flare. The eye itself further modifies perception, since night vision handles bright moving color imperfectly. For that reason, witness reports are useful but are most informative when paired with instrument records. Brightness rarely stays constant. Many fireballs pulse, flare, or shed small bright fragments that separate briefly before fading. These changes occur because the meteoroid is not usually a perfect solid body with uniform strength. Most have internal weaknesses. They may contain cracks from ancient collisions, grain boundaries between minerals, pockets of weaker material, or zones where metal and stone respond differently to heating. As the pressure from the atmosphere increases, stress builds inside the body. The leading surface is strongly heated, but the interior may remain cooler for a time. This uneven state can produce mechanical failure. A fracture opens, surface area increases, and the newly exposed material ablates more rapidly. The fireball suddenly grows brighter because more matter is interacting with the atmosphere at once. This process is called fragmentation. Fragmentation means that the original meteoroid breaks into smaller pieces during atmospheric entry. It is one of the most important reasons fireballs behave dramatically. A compact object may remain intact for much of its visible flight, and then break apart in one short violent episode. A weaker object may fragment repeatedly, producing a chain of flares and multiple luminous points moving close together. Each new fragment then has its own small disturbed envelope of hot gas and ablated material. because fragments have a greater total surface area than a single intact mass of the same volume. They can lose energy and material more quickly. This often causes a sudden brightening followed by rapid fading of the smaller pieces. The apparent size of a fireball in the sky can be misleading. Very bright objects often seem larger than they truly are because light spreads in the eye and in camera systems. The luminous head may look broader than a planet, yet the surviving solid core, if one still exists at that moment, can be far smaller than the visible glow suggests. The bright region is a product of hot gas and vaporized matter around the body, not simply the silhouette of the object itself. This is why public descriptions sometimes imagine bodies much larger than they really are. The light occupies more sky than the solid matter does. Scientists account for this by measuring brightness, trajectory, and timing rather than relying only on visual impression. The trail behind a fireball also changes as the event unfolds. A thin, glowing line may mark the path for a moment, then expand, twist, or break into luminous knots under high-altitude winds. This visible train is distinct from the solid fragments. It consists of ionized and excited gas, mixed with fine ablated material left behind in the atmosphere. In stronger events, the trail can persist long enough to deform visibly, revealing motion in upper air currents otherwise hidden from human sight. Such trains show that the fireball is not merely moving through the atmosphere like an object through empty space. It is depositing energy and material into the air and leaving behind a brief record of that interaction. Motion, color, and fragmentation together make the fireball seem alive in the sky, but the appearance remains fully physical. A bright green flare does not imply an exotic source. A sudden breakup does not imply an explosion in the ordinary chemical sense. A long path does not imply slow travel. Each feature arises from known interactions among speed, entry angle, structure, and atmospheric stress. Scientists reconstruct these events by comparing observations from different locations, estimating true velocity and geometry, and modelling how various materials behave under intense heating and pressure. In this way, the visible behaviour becomes a form of evidence. By this point in the descent, the original meteoroid has already lost some of its earlier identity as a small body in solar orbit. It is now a changing collection of luminous gas, ablated material, and perhaps several surviving fragments travelling together for a time. What the ground observer sees is the outward expression of an inward failure of the body under stress. The fireball's motion across the sky, its shifting colours, and its abrupt flares are all signs that the atmosphere is no longer only heating the object. It is testing its structure, stripping its surface, and, in many cases, breaking it apart piece by piece as the descent continues. Deeper in the atmosphere, as the fireball continues to descend, light is no longer the only outward sign of the encounter. Pressure grows stronger, the surrounding air becomes denser, and the interaction between the moving body and the atmosphere begins to produce effects that can later be heard or felt on the ground. At this stage, the fireball may still appear as a bright moving streak, but it is also becoming a source of mechanical disturbance in the air. The most important of these disturbances is the pressure wave, which forms because the body is travelling far faster than sound can move through the atmosphere. Sound is a travelling wave of pressure in air. When an object moves more slowly than sound, pressure changes can spread ahead of it. When an object moves faster, they cannot. The air is forced aside abruptly, and a compressed wave forms along the path. This is the beginning of what is often called a sonic disturbance. In simple terms, the fireball pushes through the atmosphere so rapidly that the air has no time to move gently out of the way. Instead, it is compressed into a sharp front, and that front carries energy outward. Along a long fireball path, this compressed wave can extend over a great distance. It is not experienced immediately by most ground observers because light reaches the eye much faster than sound reaches the ear. The flash is seen first, the sound. If it is strong enough and if conditions allow it to travel clearly, arrives later. This delay can create a powerful impression. A bright streak crosses the sky, and only after several seconds or even longer does a rumble, a crack, or a series of booms arrive from above or from the horizon. The delay itself is ordinary physics. Light travels so quickly that for practical human experience it is received almost at once. Sound moves far more slowly through air, and its travel time depends on the distance between the event and the observer, as well as on temperature, wind, and the layering of the atmosphere. A fireball seen far away may never produce audible sound at the ground, even if it creates a substantial pressure wave aloft. The sound may weaken before arriving, or it may be refracted, meaning bent by changes in air temperature and density, so that it passes above or away from populated areas. On other occasions, the same kind of event may produce a distinct arrival of sound over a wide region. This unevenness is one reason public reports differ so much from one fireball to another. The sounds themselves vary. Some are described as booms, some as deep rolling thunder-like noise, some as sharp cracks, and some as repeated pulses. These differences depend on the structure of the event. A body that remains coherent for longer may generate a more continuous pressure disturbance along its path. A body that breaks apart suddenly can create a more abrupt release of energy into the surrounding air. Multiple fragments can produce overlapping disturbances. Local geography and the built environment also shape what is heard. Hills, valleys, buildings, and open water can reflect or soften certain frequencies. Indoors, windows may rattle while the sky outside appears calm again. In quiet rural places, a low rumble may be heard more clearly than in cities, where traffic and machinery mask weaker sounds. One of the most striking processes in this atmospheric region is the airburst. An airburst occurs when the incoming body undergoes major fragmentation and rapid energy release, while still in the atmosphere rather than at the ground. The word does not require a chemical explosion like that of fuel or a manufactured explosive. It refers to a sudden and intense disruption of the meteoroid under aerodynamic stress. Aerodynamic stress means the force placed on the body by its rapid movement through the air. As atmospheric density increases, the pressure acting on the front and outer surfaces rises sharply. If that pressure exceeds the structural strength of the body, the object can fail catastrophically. When this happens, the body fragments into many pieces. Surface area increases enormously, ablation accelerates, and a large amount of kinetic energy is deposited into the atmosphere over a short interval. The visible sign of such a failure is often an abrupt flare, sometimes brighter than any earlier part of the path. The mechanical sign is a strong pressure wave. In larger events, that wave can break windows, shake structures lightly, and be detected over long distances. In more modest events, it may simply produce a delayed boom. The body does not need to be large by terrestrial standards for the experience on the ground to feel unusual. A relatively small natural object, entering at high speed and breaking apart under strong atmospheric pressure, can create a moment that seems disproportionate to its size. This is one reason fireballs can feel abnormal, even when the underlying process remains natural and well within the known range of meteoroid behavior. Not every bright meteor produces an airburst of significance. Many fragment gradually rather than violently. Many deposit energy over a long enough path that no single moment dominates. Others remain too small or too high for their pressure waves to reach the ground strongly. Scientists distinguish among these cases by studying light curves, infrasound records, radar observations, satellite measurements, and witness reports. Infrasound refers to very low-frequency sound waves, below the normal range of human hearing. These waves can travel great distances through the atmosphere. Large fireball events sometimes produce infrasound that can be recorded far from the entry path. This allows researchers to estimate the energy released and compare the event with other known atmospheric entries. The deeper atmosphere therefore acts not only as a source of light, but also as a medium that transmits force. The fireball is now disturbing more than the narrow gas envelope immediately around it. It is sending organized pressure outward through the air. In some cases, this remains mostly an invisible physical consequence measured only by instruments. In other cases, it enters everyday experience through delayed sound and mild shaking. That transition from silent visual event to audible atmospheric disturbance is important because it changes how the event is remembered. Something seen only as a streak may be recalled as beautiful or strange. Something followed by a boom may be recalled as threatening, explosive, or not normal. The interpretation changes even when the process does not. Uncertainty still remains in individual cases. A witness may hear a sound and assume it came from the brightest visible flare. When the geometry of the path suggests otherwise, local echoes can make a single wave seem like several. Distant thunder, industrial noise, or aircraft can occasionally complicate reports. Scientists therefore compare many observations before drawing conclusions about the exact structure of an event. Even so, the general pattern is clear. As the fireball penetrates denser atmospheric layers, pressure waves strengthen, fragmentation can become more abrupt, and sound becomes more likely to follow the light after a delay. At this stage, the descending body is no longer simply a luminous object crossing the sky. It has become a moving source of stress in the atmosphere itself. The air is compressed, shocked, and set into wave motion. Sometimes the object breaks apart gradually, and the disturbance remains modest. Sometimes it fails suddenly and produces an airburst that concentrates brightness and pressure into one dramatic interval. The country below may experience the event only as a flash, or as a flash followed by rumbling evidence that the atmosphere has absorbed and redistributed a portion of the object's motion. What appears to the eye as a brilliant streak is now also a physical force passing through the air, shaped by altitude, structure, and speed. Below the heights where the brightest flares and strongest pressure waves often form, the atmosphere becomes denser still. In this lower region, the event changes character again. The most intense luminous phase may already be ending, and the surviving material, if any remains, no longer behaves like the brilliant fireball seen high overhead. The atmosphere has taken away a large share of the body's original kinetic energy. Fragments that survive this far are smaller, slower, and less able to keep the surrounding gas in a highly luminous state. The process is still a descent through air, but it is no longer dominated by the same extreme glow. The fireball gives way to falling debris. This change is gradual rather than sudden. A bright meteor does not switch off like a lamp. As speed decreases and the rate of energy transfer to the air falls, the visible light weakens, the hot wake fades, the ionized trail disperses. Individual fragments may still glow briefly, especially if they have only recently separated, but the overall event moves away from the brilliant upper atmosphere phase. What continues downward are the pieces that have endured enough heating and stress to remain solid. Many smaller fragments do not survive this transition. They lose mass until nothing substantial remains. Only the stronger or larger pieces can persist into denser lower air as separate falling bodies. Scientists describe the later stage of a surviving fragment as dark flight. The term means the part of the descent after luminous ablation has mostly ended. The fragment is still falling, but it is no longer producing the bright meteor light that makes it visible over long distances. In this stage, the body behaves more like an ordinary object moving through air under gravity and drag, though it remains unusual in origin and often in temperature history. Drag means resistance from air acting against motion. By the time dark flight begins, the fragment has slowed enormously compared with its entry speed. It is no longer racing through the atmosphere at cosmic velocity. Instead, it is descending under a balance of gravity, drag, and sometimes wind. This slowing is one of the most important corrections to public imagination. A meteorite that survives to the ground does not usually strike at the same speed it had when it first entered the atmosphere. The atmosphere has already removed most of that initial velocity. Surviving fragments often reach a terminal speed, meaning a speed at which drag and gravity come into near balance, and further acceleration is limited. The exact value depends on size, shape, density, and air conditions. A compact stone-sized fragment falls differently from a broad irregular piece. A dense iron-rich body resists deceleration differently from a more porous stony one. But in all cases, the lower atmosphere strongly moderates the descent. This is why small recovered meteorites can land without forming large craters. The fragments themselves are also changing as they fall. Their outer surfaces, once molten or partly molten during ablation, begin to cool rapidly in the denser lower air. This cooling produces a thin, dark exterior layer known as fusion crust. Fusion crust forms when the outermost surface melts during atmospheric entry and then solidifies again as the fragment cools. It is often dark, smooth, or slightly glassy in appearance, though it can crack or weather after landing. This crust is not thick. It is a surface skin, a record of the final hot passage through luminous flight. Beneath it, the interior of the fragment may remain much less altered than the outer appearance suggests. Contrary to common belief, a freshly fallen meteorite is usually not glowing red when it reaches the ground. During dark flight, cooling at the surface becomes effective, and the surviving fragment is often only warm or even cool enough to handle after some time. Depending on its size and the conditions of descent and recovery, the earlier intense heating is concentrated mainly at the outer surface during the luminous phase. The interior is protected by the poor thermal conductivity of many meteorite materials and by the short duration of entry heating. A person who imagines a meteorite arriving as a flaming mass of liquid rock is therefore imagining a stage that largely belongs to the upper and middle atmosphere, not to the final descent. Wind begins to matter more in this lower region, while luminous flight is governed mainly by entry geometry and extreme speed. Dark flight allows atmospheric motion to shift the falling path sideways. Different fragments can therefore land far from the precise line traced by the bright meteor in the sky. Smaller pieces are more affected by wind than larger ones. This produces a strewn field, which is the area on the ground over which fragments from one meteor event may be scattered. A strewn field is not random in shape. It often stretches along the general direction of travel, with lighter fragments falling short and heavier ones reaching farther. Winds at different heights can complicate this pattern, bending and spreading the final landing zone. Because the bright phase has ended, this part of the event is often hidden from direct observation. Witnesses may see the fireball vanish and assume the whole object has burned away, when in fact dark fragments continue downward unseen. In other cases, A few large pieces may remain visible for a little longer as dim points, especially at twilight or under very dark conditions. But such observations are less common and less reliable than the brilliant earlier sighting. For scientists searching for meteorites, the unseen nature of dark flight is a challenge. They must reconstruct it from the measured trajectory, estimated deceleration, atmospheric data, and models of wind. Good camera records and radar data can make this much more precise. Without them, the search area can become very large. This lower atmospheric stage is quiet compared with the dramatic flare of earlier descent, yet it is crucial. It determines whether any extraterrestrial material reaches the surface at all. It also shapes the form in which that material arrives. A body that fragments heavily higher up may send down many small stones. A stronger body may preserve fewer but larger fragments. Iron-rich material, being denser and often mechanically stronger, can behave differently from weaker stony matter, though many variables remain important. Observations indicate general patterns, but each event retains some individuality because entry speed, structure, fracture history, and atmospheric conditions differ. By the time the descent passes fully into falling debris, the atmosphere has done most of its work. It has transformed orbital motion into light, shock, heat, fragmentation, and then slowing. What remains are solid pieces no longer ablating strongly, no longer surrounded by a glaring envelope of luminous gas, and no longer visible across a wide region of sky. They descend through ordinary air, subject to wind and gravity, cooling as they fall. The lower atmosphere is therefore the place where the fireball ceases to be a spectacle and becomes a recovery problem, a geological specimen in transit, and sometimes a quiet stone on its way toward the ground. At the end of dark flight, if any fragments remain, the event reaches the ground. This is the point at which an atmospheric phenomenon becomes a physical object that can be touched, mapped, weighed, cut, and studied in the laboratory. A meteoroid in space becomes a meteor in the atmosphere, and if part of it survives to land, that surviving piece is called a meteorite. The distinction is simple but important. The glowing streak in the sky is not itself the meteorite. The meteorite is the solid remnant that completes the descent and comes to rest on Earth's surface. For most fireballs, no such remnant is ever found. In many cases, none survives. In others, fragments survive but fall into places where recovery is unlikely. The surface of the United States offers many different landing environments. A meteorite may fall into a forest canopy, a ploughed field, a suburban yard, a desert basin, a mountain slope, a lake, a marsh, or the open ocean beyond the coast. It may strike a road, bury itself lightly in soil, chip a roof, or disappear among ordinary rocks where no one notices it. The country's size alone makes recovery difficult. A bright fireball can be seen across several states. Yet the zone where meteorites might actually land is usually far smaller and often uncertain, unless the trajectory is recorded well. Even then, local terrain matters. A fragment that lands in open, dry desert is easier to recover than one that falls into dense vegetation or waterlogged ground. Most fireballs do not produce recoverable meteorites. Some incoming bodies are too small to survive deep entry. Others are made of fragile material that breaks apart and ablates away before dark flight can preserve substantial mass. Some produce only dust-sized remnants or stones too small to locate, even when a meteorite does reach the ground. Successful recovery depends on speed of reporting, weather, land access, and the ability to model the fall accurately. Rain can darken soil and hide fresh stones. Snow can bury small fragments. Ploughed land can disturb the surface. Urban areas introduce confusion because many black or metallic fragments already exist in ordinary human environments. A true meteorite must be distinguished from industrial slag, roofing material, furnace byproducts, road debris, and countless local stones. When a meteorite is recovered soon after a fall, it often shows a dark fusion crust formed during the last hot phase of entry. This crust can make the stone stand out from surrounding material, especially if it lands on pale ground. Fresh falls may also have shallow thumbprint-like surface depressions called regmaglypts, produced by uneven ablation and flow around the body. Yet these features vary, and not every meteorite is easy to recognize by sight alone. Stony meteorites are often heavier than common terrestrial rocks of the same size, but not always by a dramatic amount. Iron meteorites are much denser and easier to distinguish if recovered whole, though they are less common than stony types. Simple field tests can help, but reliable identification usually requires expert examination and laboratory confirmation. The ground effects of a meteorite fall are usually modest. Small fragments may strike with enough force to make a pit, crack pavement, dent metal, or penetrate roofs, but they do not ordinarily behave like the enormous impacts associated with large craters in deep geological time. By the time a surviving stone reaches the lower atmosphere and enters dark flight, most of its cosmic speed has already been lost. What remains is still significant, especially for a compact dense object, but it is not the original entry velocity. This is why meteorites can be recovered intact. A surviving fragment may bury itself a short distance into soil or sand, or it may come to rest on the surface if the ground is hard enough and the mass is small enough. Scientists treat a witnessed fall differently from an isolated old find. A witnessed fall is valuable because the timing is known, the atmospheric path may be reconstructed, and weathering has not yet altered the material much. Such meteorites preserve delicate chemical and mineral information more clearly than stones that have lain for years or centuries in soil. Moisture, oxygen, microbes, and temperature cycles can all change a meteorite after it lands. Metal grains can rust. Fusion crust can crack. Soluble salts can move through pores. For this reason, rapid recovery matters. A fresh meteorite is not simply a curiosity from the sky. It is a time-sensitive sample from outside Earth, and its scientific value is greatest before terrestrial alteration becomes strong. The search for fallen meteorites often begins with eyewitness reports and camera records. Investigators compare viewing angles, timing, brightness, and sometimes sound delays to estimate the luminous path and the likely onset of dark flight. Atmospheric wind data are then used to model where fragments may have drifted. Searchers walk fields, scan open land, and sometimes use drones or trained observers. In favourable cases, multiple stones are recovered along a stretched landing area that reflects the final stages of fragmentation and descent. This area, the strewn field, preserves a kind of last atmospheric sorting. Smaller pieces tend to fall earlier and closer to the point where dark flight begins, while larger pieces often travel farther downrange before landing. The public imagination often expects a dramatic impact site, but most meteorite falls are quieter than the fireball that precedes them. The sky event commands attention because it is bright and sudden. The ground event may be nothing more than a new dark stone in grass or soil. Rarely, a meteorite strikes property or, in very unusual cases, comes dangerously close to people. Such events receive broad attention because direct impacts on human structures are uncommon. The rarity of these incidents, however, should not obscure the ordinary outcome. Most meteorites land where no one is present and where no obvious damage occurs. The atmosphere has already done the greater part of the work, and the surface receives only the remaining fragments. This surface stage is where scientific certainty can become much stronger. A recovered meteorite can be measured directly. Its density, mineral composition, isotopic ratios, and internal textures can be studied in detail. The rock is no longer inferred only from light and trajectory. It becomes evidence in hand. Yet the absence of recovery does not mean a fireball was unreal or unimportant. Many well-observed fireballs leave no findable meteorites, either because nothing survived or because the landing environment defeats the search. In that sense, the ground is selective. It does not receive every bright event in the same way. What reaches the surface, then, is the residue of a long filtering process. Space provides the original body. The atmosphere tests it through heat, pressure, and fragmentation. The lower air slows and cools what remains. The ground finally receives only the pieces strong enough and fortunate enough to survive that passage. A meteorite resting on American soil is therefore not simply a stone from the sky. It is the final physical remnant of an event that began far beyond weather and clouds, became light in the upper atmosphere, turned into falling debris below, and ended as matter quiet enough to lie among ordinary earthly materials until someone notices that it does not belong. Once a meteorite has been recovered from the ground, attention turns from the path it followed to the substance it contains. The outside records its brief passage through the atmosphere, but the inside preserves a much older history. This inward step moves from landing and surface form into material structure. A meteorite is not a single uniform kind of stone. It belongs to a group of natural samples formed under very different conditions in the early solar system, and later altered by heating, collision, melting, or chemical change. Scientists study these materials because they carry evidence of processes that took place long before Earth acquired its present surface. The fragment found after a fireball is therefore both a remnant of a recent atmospheric event and a relic of ancient formation. The broadest division is between stony meteorites, iron meteorites, and stony iron meteorites. Stony meteorites are by far the most common among witnessed falls and recovered finds. They are made mostly of silicate minerals, which are minerals built from silicon and oxygen combined with metals such as magnesium and iron. On Earth, many common rocks are also rich in silicates, so a stony meteorite may not seem unusual at first glance. Yet its internal textures and chemistry often reveal that it formed in a different environment from ordinary terrestrial rocks. Iron meteorites consist mainly of metallic iron mixed with nickel. They are much denser than most rocks on Earth, and often survive weathering and atmospheric passage in distinctive ways. Stony iron meteorites contain significant amounts of both silicate material and metal. They are less common, and often especially striking in cut and polished form, where metal and crystal-rich regions can appear side by side. Among stony meteorites, one major group is the chondrites. A chondrite is a meteorite that contains small rounded grains called chondrules. Chondrules are tiny once molten droplets that formed very early in solar system history and later became incorporated into larger bodies. Under a microscope or in a cut surface, they appear as small rounded structures embedded in a finer matrix. Their presence matters because it shows that the meteorite comes from material that did not undergo complete melting after those droplets formed. In other words, the rock preserves primitive ingredients from the early solar system. Chondrites are therefore especially valuable for understanding the original building materials from which planets and smaller bodies formed. Not all stony meteorites retain such primitive textures. Some are chondrites, meaning they lack chondrules, and instead come from bodies that experienced enough heating and melting to separate and rework their materials. These meteorites resemble igneous rocks more than primitive aggregates. An igneous rock is a rock formed from molten material that cools and solidifies. Achondrites indicate that their parent bodies underwent internal heating, strong enough to drive geological differentiation, which means the separation of material into different layers or compositions. Some achondrites are linked to the crusts or mantles of small differentiated bodies. A few rare examples have even been identified as originating from the Moon or Mars, based on their chemistry and trapped gas signatures. Those are exceptional cases, but they show how varied meteorite materials can be. Iron meteorites tell a different story. Their metal-rich composition suggests formation within the cores of larger parent bodies that once became hot enough for metal to separate from silicate rock and sink inward. If such a body was later broken apart by collision, fragments of its core could remain as iron meteorites. When polished and etched in the laboratory, many iron meteorites display interlocking crystal patterns formed by extremely slow cooling over immense timescales. These patterns are not produced in ordinary industrial metal and help confirm the extraterrestrial origin of the sample. Their presence shows that some meteorites come not from the untouched outer parts of primitive bodies, but from deep internal regions that once lay inside larger asteroids. Stony iron meteorites occupy a middle ground in composition and often reflect boundary zones within differentiated bodies. Some contain large transparent or translucent crystals of olivine, a green silicate mineral, set within a metal framework. Others show broken mixtures of metal and rock suggesting complex impact histories. These meteorites are uncommon, yet they provide direct evidence that some parent bodies developed internal structures with metal-rich and silicate-rich regions in contact. Such evidence is important because it reveals that small bodies in the early solar system were not always simple rubble. Some were dynamic enough to melt internally and separate into layered forms before later collisions broke them apart. Material details within meteorites help scientists infer both origin and later history. Grain size, mineral chemistry, oxidation state, shock features, and isotopic composition all matter. Shock features are microscopic or structural signs that the rock has experienced strong impact pressure. These can include fractures, deformed minerals, or melt veins formed during collisions between parent bodies. Many meteorites have been shocked to some degree, which is not surprising in a solar system where impacts are common over long timescales. Weathering on Earth can overprint some of these features, but fresh falls often preserve them clearly enough for classification. Scientists use standardized schemes to sort meteorites by type, mineral proportions, and degree of alteration. This classification is careful work because outward appearance alone can mislead. One common misunderstanding is that all meteorites are rich in metal and strongly magnetic. Some are, but many stony meteorites contain only modest metal content and may respond weakly to a magnet or not in an obvious way under simple field conditions. Another misunderstanding is that all meteorites look burnt through their entire interior. In reality, the dark fusion crust is usually only a thin exterior layer formed during entry. When a meteorite is cut open, the inside may be grey, pale, greenish, speckled, or metallic depending on type. The interior is where the deeper story lies. It records mineral formation, thermal history, aqueous alteration in some cases, and impact processing over vast spans of time. Aqueous alteration is another important process in some meteorites, especially certain carbon-rich chondrites. The term means chemical change caused by interaction with liquid water inside the parent body long ago. It does not imply oceans or rivers in the ordinary earthly sense. Rather, It suggests that small bodies containing ice once warmed enough for water to circulate briefly through their interiors, altering minerals and creating new compounds. These meteorites are especially significant because they preserve information about water-bearing chemistry in the early solar system. Some also contain organic molecules formed through non-biological processes. Such material does not indicate life, but it does show that carbon chemistry in space can become complex. In this inward examination, the meteorite changes from a fallen object into a material archive, its category, texture, minerals, metal content, and chemical signatures all place it within a broader history of solar system formation and transformation. The fireball that draws public attention lasts only moments. The stone that remains may have held its internal record for billions of years. By studying that record, scientists move from the brief drama of atmospheric entry to the much older processes that form the matter itself. The recovered fragment becomes a sample of primitive dust, melted crust, metallic core, altered rock, or mixed boundary material. Its arrival in the United States may be recent, but its substance belongs to a far deeper time, preserved within the small mass that survives descent and comes to rest on Earth. From the material inside recovered meteorites, the path of explanation moves outward only in age and history, but inward in origin, toward the larger bodies from which these fragments come. A meteorite is a small sample, yet it usually begins as part of something much larger. The parent body is that larger source object from which the meteoroid fragment ultimately separates. In most cases, parent bodies are asteroids. In fewer cases, especially for fine meteoroid streams rather than recoverable meteorites, the source may be a comet or a body with comet-like history. This stage of the story remains within the solar system, but it narrows from the wide background of debris toward the specific kinds of bodies that supply the material later seen as fireballs over the United States. Asteroids are natural bodies that orbit the Sun and are made mostly of rock, metal, or a mixture of both. Many lie in the main asteroid belt between Mars and Jupiter, though that region is not a packed swarm in the way popular images sometimes suggest. The bodies are separated by vast distances, and collisions between large asteroids are infrequent on human timescales. Yet over the age of the solar system, collisions have been more than sufficient to break bodies apart, create families of fragments, and maintain a supply of smaller material. Some of these fragments gradually move into Earth-crossing orbits through a combination of gravitational interactions and subtle long-term orbital effects. When one of those fragments eventually reaches Earth's atmosphere, the fireball is the final visible outcome of a process that may have begun millions of years earlier. Parent bodies differ greatly in structure. Some asteroids appear to be relatively intact rocky bodies. Others are fractured remnants of earlier collisions. Some may be loose aggregates of rubble held together mainly by gravity, while others preserve more coherent internal strength. These differences matter because the internal character of the parent body influences the properties of the fragments produced when impacts occur. A compact differentiated body can yield metal-rich pieces from its core, stony pieces from its crust, and mixed pieces from boundary zones. A primitive, undifferentiated body can yield chondritic fragments that preserve ancient early solar system material. The meteorites recovered on Earth, therefore, do not all represent the same level of processing. Some come from bodies that remained comparatively simple. Others come from bodies that once had internal layering and geological change. The history of heating inside parent bodies is especially important. In the early solar system, some small bodies became warm enough from radioactive decay and impact energy to experience melting, mineral change, or partial separation of materials. If melting became extensive, metal could sink inward and silicate-rich material could remain above, creating differentiated structure. If heating remained limited, more primitive textures could survive. This helps explain why some meteorites are chondritic and some are achondritic, why some are metallic and some are mixed. The parent body acts as the environment in which these internal differences form. When later collisions break that body apart, the fragments preserve evidence of those older internal conditions. Collisions are central to this parent body story. A meteoroid that later becomes a fireball is often not a direct unbroken remnant from the earliest formation stage of its parent body. Instead, it may be a fragment produced by one or more impacts. These impacts can shatter, melt, compress, or reassemble material. Some meteorites contain breccias, which are rocks made of broken fragments cemented together by later events. A breccia records a history of breakage and rejoining, often caused by impact processes on an asteroid surface or within a fragmented body. Such textures reveal that parent bodies are not quiet storage containers. They are active participants in a long collisional history that reshapes their material again and again. Comets contribute differently. A comet contains dust, rock, and volatile frozen materials, especially in its colder outer regions when far from the Sun. As it approaches the inner solar system, solar heating releases gas and frees embedded dust and small particles. These are then spread along the comet's orbit, forming streams that Earth may later encounter as meteor showers. Most visible meteors from well-known annual showers are thought to come from this kind of source. Their particles are often too small and fragile to survive as meteorites. Even when a fireball occurs during a shower, recovery on the ground is less likely if the material is weak and porous. For this reason, many fireballs that produce recovered meteorites are associated more often with asteroidal fragments than with classic cometary dust trails. Although the boundary is not absolute and nature allows a range of intermediate properties, some parent bodies are identified more confidently than others. When a fireball is recorded from multiple stations and its pre-entry orbit is reconstructed, scientists can compare that orbit with known asteroid populations and, in rare cases, with specific near-Earth objects. Usually the result is not a firm naming of one exact source object, but an assignment to a general orbital class or source region. For example, a meteoroid may show an orbit consistent with origin in the inner main belt followed by transfer through a resonance, which is a region where repeated gravitational influences can alter an orbit efficiently. Jupiter plays an especially important role in shaping such resonances. Through these gravitational pathways, fragments from the asteroid belt can slowly evolve into orbits that cross Earth's path. Resonance is an important term here. In orbital dynamics, a resonance occurs when the period of one body's orbit relates simply to that of another, allowing repeated gravitational nudges to accumulate over time. These nudges do not usually fling a fragment directly toward Earth in a single dramatic moment. Instead, they gradually change the orbit. Over long intervals, a fragment that once stayed safely in the asteroid belt may be shifted into a more elongated path that carries it inward. Once in the near-Earth population, further encounters and perturbations can continue to modify the orbit until atmospheric entry becomes possible. The fireball observed from the ground is therefore the final short chapter of a much longer orbital evolution controlled by collisions, heating history, and gravitational transport. Recovered meteorites also help link fragments back to broad parent body classes through spectroscopy and chemistry. Spectroscopy is the study of how matter interacts with light. Telescopes can measure the reflected light of asteroids and infer general surface composition. When those measurements are compared with laboratory studies of meteorites, certain matches emerge. These matches are not always perfect because asteroid surfaces weather under space exposure and do not always reflect the exact interior properties of fallen fragments. Even so, strong patterns exist. Some meteorite groups correspond well to particular asteroid types, supporting the view that Earth's meteorites are direct samples of the diverse small bodies orbiting the Sun. By this stage, the fireball over the United States has been traced inward beyond the atmosphere, beyond the falling stone, and beyond the mineral grains inside it, to the larger worlds of origin within the solar system. These parent bodies are not large planets, but neither are they trivial pebbles. They are the reservoirs from which meteoroid fragments are supplied. Some are primitive and preserve early dust aggregates. Some are differentiated and preserve evidence of melting and internal layering. Some shed material through catastrophic collision. Some release dust through cometary activity. All contribute in different ways to the population of small bodies that occasionally meets Earth. What flashes briefly across an American sky may therefore be the last visible remnant of an ancient asteroid crust, a metallic core fragment, a primitive undifferentiated body, or a fragile stream particle long separated from a comet. The light is brief, but the source lies in the enduring architecture of the solar system. By the time the explanation reaches recent attention and public awareness, the physical path of the meteoroid has already been traced from space to atmosphere, from atmosphere to falling fragments, and from fragments to parent bodies in the solar system. What remains is to examine why fireballs can seem more frequent in the present day, especially over a large country such as the United States, even when the underlying natural process may not have changed in any dramatic way. This part of the story concerns observation rather than origin. It does not ask what fireballs are made of or how they shine, but how they come to be noticed, recorded, shared, and remembered. In that sense, it remains close to Earth, close to the human layer of the event. The first and simplest point is that the modern sky is watched more often than the sky of earlier decades. A bright fireball once depended heavily on chance observation. Someone needed to be outside, looking in the right direction, under clear enough skies, at the right moment. Many events were certainly seen, especially the brightest ones, but many others passed over sparsely populated areas, or over sleeping communities, or behind clouds, leaving no broad public record. Today the situation is different. Cameras are common, automatic, and widely distributed. Mobile phones, traffic cameras, security systems, weather cameras, and scientific all-sky networks all contribute. Most of these are not built for meteor research, yet they still capture evidence. A fireball that once might have lived only in memory can now appear in several videos within minutes. This growth in recording technology changes public perception strongly. It increases the number of confirmed events, but it also increases the visibility of events that would once have remained local. A bright meteor over one state can now be viewed by people across the country before the night has ended. The event becomes not only an observation but also a shared media object. This sharing creates a sense of accumulation. One fireball is no longer one sighting by one group. It becomes many clips, many witness accounts, many reposted images, and many headlines. The sky has not necessarily become more active in a physical sense. It has become more connected to systems of recording and communication. Scientific observation has also improved. Dedicated fireball networks now use calibrated cameras to measure trajectories, brightness, and sometimes the likely fall area for surviving meteorites. Radar can detect some types of debris trails, Satellites can observe bright atmospheric entries, especially larger bolides, which are exceptionally bright fireballs. A bolide is a very bright meteor, often associated with fragmentation or strong flaring during entry. The boundary between fireball and bolide can vary somewhat in usage, but the important point is that modern instruments register more events and characterize them better than older methods allowed. What earlier generations may have described only as a strange streak can now be timed, triangulated, and analyzed quantitatively. The public environment around those observations matters just as much. New systems now favor rapid circulation of dramatic visual events. A brief bright fireball crossing a night sky is well suited to this pattern because it is visually clear, sudden, and easy to clip into short video form. Social media multiplies that effect. When a fireball is posted widely, people begin to search memory for similar stories, and recent examples feel closer together than they are. This is a common feature of human attention. Events that are vivid and highly shareable create a strong impression of increase. Scientists take this into account when they compare present-day reporting with older records. A rise in reports does not automatically mean a rise in physical frequency. Seasonal factors add another layer. The United States experiences large differences in weather, daylight length, and nighttime activity across the year. In some seasons, more people are outdoors at dusk or after dark. In some seasons, clearer skies improve visibility over large regions. Meteor showers also return at predictable times, increasing ordinary meteor activity and occasionally producing bright events that attract special attention. A period that contains both clear skies and active public sharing can therefore feel unusually rich in fireballs even if it falls within expected natural variation. Observations indicate that meteor activity is not evenly distributed across every night of the year. But this unevenness is mostly well understood and does not by itself imply something abnormal. Population distribution influences perception as well. A bright fireball over a rural desert may be recorded beautifully by a few instruments and scarcely discussed outside scientific circles. A similar event over a dense urban corridor may be witnessed by thousands of people and generate immediate reports from many angles. The physical event may be comparable, yet the social footprint differs enormously. The United States contains both thinly observed dark regions and heavily populated bright regions, and the contrast between them affects the national impression of how often fireballs occur. An event becomes part of public experience not only by happening, but by happening where enough people can see it, record it, and exchange accounts. There is also the matter of improved classification. In earlier periods, a witness might describe any sudden light as a shooting star, a falling object, or something unexplained. Today, scientific organizations and public tracking systems collect reports systematically and compare them with known meteor activity, aircraft, satellite re-entries, and other possibilities. This helps convert scattered impressions into organized data. More events are recognized correctly as fireballs rather than left ambiguous. In one sense, this increases the counted number. In another sense, it reduces mystery by placing the event inside a known category. Both effects happen at once. More is counted, but more is also explained. What remains uncertain is whether shorter-term clustering of bright fireballs reflects a real change in incoming objects or merely a change in detection and reporting. In some cases, several bright events may occur within a relatively brief interval over North America simply by ordinary statistical variation. Space delivers meteoroids continuously, but not in perfectly even spacing. A few bright arrivals close together in time do not automatically indicate a new hazard, or unusual celestial condition. On the other hand, observations can sometimes identify periods when Earth encounters denser debris associated with known streams, or when a specific source region contributes more visible activity. The important scientific habit is caution. Apparent increase must be compared against instrument coverage, sky conditions, public reporting, and long-term records before any claim of real physical change is justified. This caution matters especially when phrases such as "not normal" enter public discussion. A pattern may feel abnormal because it is newly visible, newly shared, or newly measured. That feeling is understandable, but feeling alone is not a scientific conclusion. Scientists compare present rates with historical fireball databases, with known shower behavior, and with the growth of camera coverage. They ask whether the number of well-observed events exceeds what improved detection would predict. In some cases, the answer remains uncertain because older records are incomplete and modern coverage is uneven. What is clear is that the current era produces far richer evidence than the past. So the sense of recent increase arises from several overlapping causes: more cameras, faster communication, better scientific networks, stronger public attention, seasonal visibility, and uneven population density beneath the sky. None of these causes requires a dramatic change in the solar system. The country may indeed notice more fireballs now than it once did, but much of that increase belongs to awareness, documentation, and comparison rather than to a sudden transformation of nature itself. The modern United States lives under a more observed sky. That is enough to make familiar cosmic events feel newly frequent, newly close, and newly significant, even when they remain part of the long-standing exchange between Earth and the small bodies that continue to cross its path. When scientists describe an event or a pattern as not normal, they do not usually mean merely surprising, memorable, or dramatic. In science, normality is not decided by emotional response. It is decided by comparison with a baseline. A baseline is the established range of behavior drawn from past observations, measured rates, known physical processes, and the limits of ordinary variation. This means that the phrase "not normal" has value only if there is enough evidence to define what normal has been. In the case of fireballs over the United States, this requires more than a few striking videos or several widely discussed events close together in time. It requires records, classification, measurement, and statistical care. The first step in defining normal fireball activity is to separate categories of observation. Scientists distinguish between all meteors, bright meteors, fireballs, and the rare larger events sometimes called bolides. They also distinguish between raw reports and verified detections. A raw report may come from a witness who sees a bright streak and submits the time, direction, and appearance. Such reports are useful, but they vary in reliability. Human estimates of brightness, distance, and duration can be strongly shaped by darkness, surprise, and perspective. A verified detection comes from instrument data, multiple agreeing reports, or both. This difference matters because a rise in raw reports can reflect changes in public awareness just as easily as changes in the sky itself. A proper baseline must also account for observing conditions. A cloudy week cannot be compared directly with a clear week. A period before widespread camera coverage cannot be compared simply with a period after automated networks become common. Population density matters, as does the geographic spread of observation systems. A fireball over a densely observed corridor is more likely to be recorded and widely reported than one over remote land or water. Scientists therefore adjust their expectations according to where and when the sky is being watched. In other words, Normal is never just the number of events written down. It is the number of events written down relative to the opportunities for seeing them. Long-term records help build this context. Fireball databases compiled from observation networks, public reports, satellite measurements, and meteor surveys allow researchers to ask whether current activity falls within expected variation. Expected variation means the ordinary rise and fall that occurs even when there is no new physical cause. Random processes are often clumpy. Several bright events may happen close together by chance, then be followed by a long, quieter interval. A short cluster can feel unusual without being statistically rare. Statistics is the part of mathematics that examines patterns in data, especially the difference between meaningful change and ordinary fluctuation. In fireball studies, statistics helps determine whether an apparent surge is larger than baseline variation would reasonably allow. This does not mean that unusual patterns are impossible. Scientists do recognize true anomalies when the data support them. An anomaly is a deviation from the expected pattern that remains significant after observational bias and ordinary variability have been considered. For meteors, a true anomaly might involve an unexpected outburst from a known stream, the appearance of activity linked to a newly recognized debris trail, or a measured number of bright entries clearly above model expectations for the available observing coverage. Such cases are investigated carefully because they may reveal something new about meteoroid streams, orbital evolution, or the fragmentation history of a parent body. But the standard for that conclusion is high. It rests on evidence, not on the intensity of public reaction. Measurement networks are central to this judgment. All sky camera systems record timing, trajectory, apparent brightness, and motion across the sky. When two or more stations observe the same event, scientists can triangulate the path. Triangulation means determining a position or track by comparing views from different locations. From this, they can estimate entry speed, altitude, and sometimes the likely pre-entry orbit. These measurements turn a dramatic sighting into a data point that can be compared with hundreds or thousands of others. Without such networks, normality is harder to define because memory and anecdote are uneven. With them, comparison becomes more disciplined. Satellite observations provide another layer, especially for the brightest entries. These records can detect atmospheric energy release over broad regions and help estimate the size and speed of the incoming object. Infrasound stations add further evidence for larger events that produce strong low-frequency waves in the atmosphere. Together, these systems reduce uncertainty. They do not remove it entirely. Because coverage is still incomplete and different instruments are sensitive to different parts of the event, but they allow a more objective view than public reporting alone. A scientist considering whether something is not normal therefore asks first what the instruments show, how complete the coverage is, and how similar past periods compare. Language becomes especially important here. In public speech, not normal often means alarming. In scientific speech, it means inconsistent with the current baseline after correction for bias and uncertainty. These are not the same thing. A fireball bright enough to rattle windows may be rare in local experience and still normal in the national record over a long enough time scale. Several bright fireballs within 1 month may feel unusual and still fall within expected statistical variation across a large country. Conversely, a less dramatic pattern might be scientifically interesting if it departs clearly from long-term measured behavior. The emotional weight of the event and the statistical weight of the pattern are related only loosely. The caution extends to headlines that frame routine celestial events as signs of a new condition. Fireballs are real atmospheric entries by natural bodies from space. They can be startling, and in rare cases they can produce damage through strong airbursts or falling meteorites. Yet rarity and local memory does not by itself make them abnormal in a national or planetary sense. The United States covers a vast area beneath an active atmosphere and a constantly changing observational network. Over such a region, bright entries will occur from time to time. What science seeks to determine is whether the rate, source, distribution, or energy of those entries has shifted beyond expected bounds. Uncertainty remains part of that determination. Older records may undercount events because fewer instruments existed. Public databases may be influenced by media attention. Some instrument networks have expanded over time, changing the effective sensitivity of the record. Researchers try to account for these factors, but the corrections are not always exact. For this reason, careful scientists often use measured language. Observations may suggest a pattern. Current evidence may indicate no strong departure from expectation. It may remain uncertain whether an apparent increase reflects a physical change or a reporting change. Such wording is not hesitation for its own sake. It reflects the real limits of the data. So when science asks whether recent fireballs are not normal, it asks a narrow and disciplined question. It compares present observations with long-term baselines, adjusts for where and how the sky is being watched, separates verified events from raw impressions, and tests whether the apparent pattern exceeds ordinary fluctuation. Only after that process can the phrase carry scientific meaning. In this way, not normal becomes less a dramatic claim than a measured conclusion reserved for cases where the evidence shows that the current pattern truly stands apart from the expected background of fireball activity over Earth and over the United States. When the evidence gathered so far is brought together, a careful picture begins to form. Fireballs over the United States are real, natural atmospheric events produced when meteoroids enter Earth's atmosphere at high speed, compress the air, heat strongly, ablate, and often fragment. This much is well established. It is also well established that Earth encounters extraterrestrial material continually, that bright meteors are an expected part of that ongoing process, and that fireballs can appear over any large region of the planet, including North America. Observations from camera networks, satellite records, radar, infrasound systems, recovered meteorites, and long-running public report databases all support this general framework. The central uncertainty is not whether fireballs are happening, but whether a recent impression of increase represents a genuine shift in physical activity or a shift in how often such events are seen, recorded, and shared. What is known with strong confidence begins at the broadest level. Earth moves through a natural population of dust, stone, and metal fragments left by asteroid collisions, cometary shedding, and long-term orbital evolution in the solar system. Some of this material arrives in organized streams associated with annual meteor showers. Some arrives as sporadic meteoroids not tied to a well-known shower. Both categories are normal. It is also known that most meteoroids are small and harmless, and that only a minority produce bright fireballs visible over wide areas. An even smaller fraction survives to the ground as meteorites. These are not controversial points. They are consistent across modern observational astronomy and planetary science. It is also known that the atmosphere is highly effective as a protective layer. Most incoming objects are slowed, fragmented, or fully consumed before they can reach the surface. Even when a fireball is bright and dramatic, the original body may be relatively modest in size. A small meteoroid entering at high speed can release enough energy to create an impressive luminous event. This is one reason public intuition often overestimates the size of the incoming object. The brightness belongs to the interaction of motion, atmosphere, heat, and ablated material. it does not map simply onto the dimensions of the original stone. Scientists are confident about this because countless observed fireballs have been reconstructed and compared with recovered meteorites or instrument-derived energy estimates. Another point known with confidence is that modern detection has changed sharply. The United States now lies beneath a far denser observational web than in the past. Scientific camera networks have expanded. Public reporting systems are easier to access. Security cameras, dashboard cameras, mobile phones, and weather cameras continuously sample the sky by accident or by design. This means that any comparison between recent years and earlier decades must be handled cautiously. A higher number of documented fireballs today does not by itself prove that more meteoroids are entering the atmosphere. It may simply mean that more entries are being detected and distributed through media systems that did not exist in earlier form. What remains uncertain is the exact degree to which recent public concern corresponds to a measurable departure from long-term expectations. Observations indicate that bright fireballs do cluster at times, because meteor activity is not perfectly uniform and because random processes often produce uneven spacing. A few notable events close together in time can happen without requiring a new physical cause. It remains uncertain, in any specific short period that draws public attention, whether the apparent clustering is statistically unusual once observational bias is removed. To answer that properly, scientists must compare the number, brightness, timing, and source characteristics of recent events against long records corrected for changes in coverage. That kind of analysis is careful and often slower than the public conversation around dramatic videos. There is similar uncertainty in linking individual fireballs to specific source populations. In some cases, if trajectory data are strong and the timing aligns with a known meteor shower, the origin can be assigned with reasonable confidence to a stream. In other cases, a reconstructed orbit may indicate a general asteroidal source region, but many events remain only broadly classified. The pre-entry orbit may not be known precisely enough, or the observations may be incomplete. Scientists can often say that a body likely had an asteroidal orbit or that it was not obviously associated with a major shower, but the exact parent body may remain unknown. This is not failure. It is a realistic limit of available data for brief events that occur unexpectedly over a large atmosphere. There is also uncertainty in the public phrase "not normal" itself. In ordinary language, it may suggest danger, escalation, or a break from familiar nature. In scientific language, it needs a much narrower meaning. It can only mean that the observed pattern differs significantly from the established baseline after accounting for detection bias, weather, sky coverage, and reporting intensity. At present, for many public claims about recent fireball frequency, observations indicate caution rather than certainty. The events themselves are real. The feeling of increased frequency is understandable. Yet it remains uncertain in many cases whether the increase belongs to nature or to attention. This distinction is central because it separates a true change in the extraterrestrial environment from a change in human awareness under a better watched sky. Scientists are also careful about hazard. Most fireballs pose no direct danger to people on the ground. Rare larger events can produce strong airbursts, broken windows, or localized damage, and recovered meteorites can occasionally strike structures. These possibilities are real, but they remain uncommon relative to the large number of atmospheric entries that end harmlessly aloft. Observations support the view that the atmosphere protects the surface efficiently from the vast majority of incoming small bodies. It remains uncertain exactly how often any one region of the United States will experience a particularly bright or audible event in a given span of years. Because such occurrences are infrequent and unevenly observed, But the broad hazard picture is not mysterious. The risk from ordinary fireballs is low on human scales, even though the experience can be intense. So the evidence leads to a restrained conclusion. Fireballs over the United States are part of a known natural process grounded in well-understood physics and planetary history. Modern records make them more visible than before. Known meteor showers, sporadic asteroidal fragments, atmospheric entry dynamics, fragmentation, and observation bias all account for much of what people now notice. Observations indicate that recent attention does not automatically imply a new abnormal condition in the sky. At the same time, it remains uncertain in any narrowly defined public moment whether a short-term cluster exceeds expectation until proper statistical comparison is made. What is known is strong. What remains uncertain is limited and specific. The science does not support exaggeration, but it does support close watching, careful measurement, and a clear distinction between real atmospheric events and the larger human story built around noticing them. Closest to human life, closest to weather, aircraft, mountains, cities, and the breathing surface of the country, the atmosphere remains the final and most immediate region in this inward path. Everything described before now comes to rest here. The meteoroid begins far beyond ordinary air, but the event becomes visible, audible, and sometimes recoverable only because Earth is wrapped in this thin layer of gas. Without it, there would be no fireball in the familiar sense. No bright meteor streaking over the United States. No booming airburst, no slowed descent of fragments into fields or towns. There would only be silent impact from space. The atmosphere transforms that possibility. It takes incoming motion and turns most of it into light, heat, pressure, and dispersal before the surface is ever reached. This protective role is not dramatic in appearance on ordinary days. The atmosphere is transparent enough that stars can still be seen at night, and its presence is often noticed more through weather than through its deeper shielding function. Yet in physical terms, it is a substantial barrier. Even though it is thin compared with the size of the planet, it contains enough mass to slow, heat, and often destroy small bodies arriving at extreme speed. The effect depends on depth. High in the atmosphere, the air is sparse, but it is sufficient to begin compression heating and ablation. Lower down, the density rises, aerodynamic stress strengthens, fragmentation becomes more likely, and surviving pieces lose speed. By the time any fragment reaches dark flight, the atmosphere has already taken away most of the dangerous part of the entry. This protection is selective rather than absolute. Very small particles are stopped high above and may leave only faint meteors or none visible at all. Modest meteoroids can produce brilliant fireballs while still being almost entirely consumed before they reach the surface. Larger and stronger objects may survive in part as meteorites. Rare, still larger bodies can create significant airbursts, and on much longer geological timescales. Larger impacts can overcome atmospheric protection and reach the ground with major consequences. The atmosphere does not make Earth inaccessible to all extraterrestrial matter. Instead, it sorts incoming material by size, speed, angle, and strength. Most of what arrives is neutralized aloft. Only a smaller fraction completes the passage in solid form. Its protective power depends on known physical processes, not on a single simple mechanism. Compression heating raises the temperature of gas and surface material. Ablation strips away mass. Fragmentation increases exposed surface area and accelerates energy loss. Pressure waves spread energy outward into the air. Drag slows surviving fragments until they fall at far lower speeds than those of entry. Cooling in the lower atmosphere allows fusion crust to form, while preventing the interior of many fragments from heating throughout. Each of these processes belongs to the same atmospheric medium acting at different heights and densities. Together they explain why the same object that enters at cosmic speed may end as a scattered set of small stones or as nothing at all. This is why the atmosphere can be understood as both a boundary and a translator. It marks the boundary between space and surface experience, but it also translates invisible orbital motion into earthly phenomena. It turns a silent meteoroid into a visible fireball. It turns speed into brightness, structure into fragmentation, and energy into sound delayed across the landscape. It turns extraterrestrial matter into something that can be studied on the ground. In doing so, it makes the event legible to science and to ordinary human observation alike. What appears as a brief streak over the United States is the visible signature of the atmosphere at work. The sense that something is not normal often arises at this final boundary, because this is where human life meets the event. A bright fireball overhead, a delayed boom, a vibration in windows, or a dark stone recovered from soil all feel immediate and local. Yet the atmosphere shows that these local experiences are the near-surface expression of broader planetary and solar system processes. They feel sudden because the transformation happens quickly. They feel unusual because daily life does not often place human attention on high-speed entry from space. Still, the atmosphere handles such arrivals according to stable physical laws. It does not improvise. It responds according to density, pressure, temperature, and motion. Across the United States, this layer of air is uneven in weather but consistent in function. Over deserts and coasts, over plains and forests, over crowded cities and remote mountain land, it performs the same broad work. It filters sunlight by day, supports weather and climate, carries sound and water, and at times intercepts material from space. Most nights its shielding role is invisible. Then, on a few nights, that role becomes briefly luminous, a fireball appears, and the atmosphere reveals itself not only as air to be breathed and weather to be endured, but as a planetary defense system operating in plain sight for a few seconds. In this final region, the subject settles into its simplest truth. Fireballs hit the atmosphere over the United States because Earth moves through a solar system that contains natural debris. Scientists watch these events because they reveal the interaction of small bodies with air, and because they provide samples and measurements that connect the ground to the wider history of the solar system. Observations indicate that the events themselves are real and expected, while it remains uncertain in some cases whether public impressions of increase reflect true physical change or improved detection. What does not remain uncertain is the atmosphere's central role. It is the medium that protects the surface, records the encounter, and determines whether an arriving body becomes only light and sound, or light, sound, and stone. The sky above the United States returns to its usual quiet after a fireball passes. The light fades, the trail thins and disappears into cold upper air. Any delayed sound arrives and then is gone as well, leaving the land, the roads, the roofs, the fields, and the sleeping cities beneath the same atmosphere that was there before. Yet the event leaves behind a clearer sense of scale. Earth is not isolated. It moves through a solar system still filled with fragments of its long formation, and from time to time some of those fragments meet the planet in visible ways. Most of the time, the atmosphere handles these meetings without consequence at the surface. It glows for a moment, carries away energy, slows what can be slowed, and disperses what can be dispersed. Only rarely does a small remnant continue all the way down to become a stone on the ground. This is the ordinary pattern, quiet in its repetition even when dramatic in appearance. Observations indicate that modern life notices more of these moments because the sky is watched more often and shared more widely. It remains uncertain, in some periods of heightened attention, whether the sense of increase belongs to nature itself or to the growing ability to record what was once missed. What remains steady is the deeper relationship between space and air, motion and light, falling stone and protective atmosphere. A fireball is brief, but it joins many layers of reality at once. It belongs to ancient parent bodies, to solar orbits, to atmospheric physics, to human perception, and sometimes to the ground itself. After the brightness is gone, the larger setting remains calm. Earth continues along its path. The atmosphere continues its silent work. The night sky resumes its ordinary appearance, holding within it the possibility that another small fragment, on another night, may enter, shine for a few seconds, and pass back into darkness.